Hi everyone. This is a communication theory course, and this is the first lecture of chapter 3. The chapter 3 will cover about the digital modulations for the transmitter, and after chapter 3 we'll have chapter 4 about the detection at the receiver. So in chapter 3, we will discuss first the signal space representation of waveform. Why do we need modulations, and what is digital modulations? Okay, and then we will so that would be the signal space representation that gives the fundamental concepts of digital modulations, from continuous waveform to the digital signaling. And with this fundamental concept, we will discuss the modulations, the signal schemes, how we do different types of modulations. And based in this book, that the different types of modulation are classified into two categories: the modulation without memory and the modulation with memory. The modulation without memory is that means that the modulation does not depend on the past symbols, past the modulation, or it depends on the current signaling, the current information. And then we will discuss the MRA, PAM, amplitude modulation, the phase shift keying modulation, and the QAM, QAM, quadruple amplitude modulation. And we'll discuss using the frequency for MRA orthogonal signaling, and then we'll discuss the bi-orthogonal signaling, and then the simplex signaling concepts. And the second category of the modulation are with memory. That means that the modulation has, every modulation has dependency with other modulation symbols, or with the past symbols. And so here we discuss two types: the linear modulation with memory and the nonlinear modulation with memory. And after discuss all different types of modulation, and they are all this modulation has different properties and different pros and cons. And after discussion of these different types of modulation, then we discuss the power spectral density of different modulations. Different modulations that they show different power spectral density. Okay, so power spectral density is an important property for modulation, because it defines how much bandwidth is needed to transmit the certain types of modulation symbols. Okay, that gives the chapter 3. Okay, first the fundamentals of modulation, digital modulation, is the signal space representation of waveform. Say given signal waveforms of S1T, S2T, to SMT. Say we have m different waveform, different types of waveform, and each waveform would represent different type of message. So we have m different type of message to deliver, and the system design from the system design perspective, we need to ask what is the necessary signal space to represent the waveforms. Okay, it's not necessary to have a signal space that has m dimensional. Okay, and so there's we can have so we are asking what is the necessary signal space. So with the basis functions, say we have phi1, phi2, and phi n, and n is smaller than m, the number of waveforms. So the transmission signal, or SIT, I from 1 to m. So we have m different types of transmission signals. And suppose we have a sufficient set of basis function, then the signal waveform SMT can be represented by the linear combinations of these basis functions. And these basis functions are also normal to each other. By also normal, we means that the inner product, okay, the inner product of this basis function is 1 if there's for the same basis function, or 0 for different basis function, the inner product. That means also normal. And the coefficient Sij, that means that the projection or inner product of waveform SIT onto basis phi jt. Okay, the projection or the inner product of the waveform onto basis. Okay, so I from 1 to m and j from 1 to n. Okay, then so you can see that SIT is the SIT, certain waveform has a projection onto different bases, right? The projection onto different bases with the projection value SIT, and by combination of all the projections onto different bases, then we can synthesize SIT, each waveform. So the signal space of this base, the expansion of the basis function that spans the signal space of SIT, okay, for all the waveform. Okay, then we say we have the signal space represented by this set of bases phi 1 to phi n. Let me give you an example. For example, that we have in here we have n equal to 3. We have phi 1, phi 2, and phi 3. That makes the three-dimensional signal space. And we have eight waveforms. This m equal to 8, 8 waveforms. And each waveform has a projection onto each basis phi 1 to phi 3. And the projection will make the projection onto the signal space that gives 8 different representations of the 8 waveforms. Right. So so we have a smaller number of bases phi n to represent a large number of bases. Another example is when m equal to 4. That means that we have 4 different waveforms, right? 4 different waveforms, and we have n equal to 2 and 2 bases. On these 2 bases, two-dimensional signal space domain, we can represent 4 different waveforms by the projection value of waveform 1 onto phi 1 and phi 2. Then we have this vector S1 to represent the waveform S1t. And waveform S2t has projection onto the phi 1 and phi 2. Right. And waveform S3t has projection onto phi 1 and projection onto phi 2. And waveform S4 has projection onto phi 1 and projection onto phi 2. Okay, so we can have signal space, a finite signal space, a smaller signal space to represent all the transmission signal waveforms that we want to transmit. So you may wonder, why do we need to discuss the signal space? What does it mean? How does the signal space representation affect the system? The signal space represents the fundamental architectures of the transmitter and receiver in a communication system. Once we find the necessary signal space to represent the set of waveform, then we can use the signal space basis to define the transmitter and receiver architectures. In the transmitter, we can synthesize the transmit waveform, SIT, and there are m different waveforms, right? And these m different waveforms can be synthesized by the basis functions phi 1 to phi and t, right? And because n is usually much smaller than m, so we could have a much smaller simple architecture to synthesize the required waveform. Similarly, in the transmitter, say if we have a perfect receiving of the transmit waveform of SIT, and there are m different waveforms. At the receiver, we need to detect or identify the waveform. Then we can decompose the received signal. This received signal is unknown, right? The receiver does not know which waveform is received and need to detect. So by projection of received signal waveform onto each basis, phi 1t to phi nt, right? That do the product and do the integral, right? That's inner product, the projection onto each basis. Then we have the projection value. We have the projection value onto each basis that represent the certain waveform. So the basis that defines the receiver architecture, and based on the projection values, based on the set of projection values, we can determine which waveform is received. Okay? So therefore, the continuous waveform, there are m different continuous waveforms, can be fully represented by the signal vectors, right? By the signal vector of dimension n, a vector of length of n. And each waveform, there are m different waveforms, and each waveform would be corresponding to one vector in the signal space, right? So it's the continuous signal can be fully represented by the vector. Then the processing of the continuous signal waveform can be we can leverage on the linear algebra tools, the tool of discrete time signal processing, the mathematic tool of linear algebra of matrix vector operations to operate the signal instead of operation on the continuous signal waveform. You may wonder why we can do this. Can this digital discrete time signal vector operation can represent a continuous signal operation or not? So let's take a look at the signal vectorization. The first is the signal energy. So the signal energy can be represented by the vector, the 2 norm of the vector, or the inner product of the signal vector. Right. The signal vector is the inner product. The 2 norm of the inner product is the summation of the power of the square of all the component in the vector, right? As we can see, this summation would be equal to the integral of the square of the signal waveform, right? By replace this signal waveform, by replace by the definition of the vectorization, and we put it into here, then we can easily show that, okay, this signal energy in the continuous signal would be exactly equal to the 2 norm of the vector. So we do not have to do this continuous inner product. Instead of doing this inner product in the continuous domain, we can simply do the inner product of the vector. That makes it much easier, and also it is exactly the same. The second is the signal inner product. Remember what is the signal product for the continuous signal? That is the product of two functions and do the integral, right? That is the that defines the inner product of two functions. And these two functions, or these two waveforms, can be represented by the combination onto the signal space with the basis, right? So this is SIT, projection onto phi, and this is SKT, projection onto phi, right? So this is phi SIT, and this is SKT. And by the orthogonal property, okay, orthonormal property of phi j of the phi, of the basis, then we can easily show that this the result is the summation of the Sij and Skj, and that would be actually the inner product of these two vectors of Si and vector Sk. And so the signal energy is actually a special case of the signal inner product when k equal to I. Okay, when k equal to I, that gives the special case that is actually the signal energy. The third example is the signal distance. So how we calculate the distance of two waveforms or two functions is the difference of these two functions square and take the integral that represent the distance, okay, the distance of these two, the square of the distance actually of these two functions. And then by the definition of the projection of the signal representation of the SIT and the signal representation of SKT onto the signal space, then we can easily show that the distance would be equal to the distance of these two vectors. Okay, of these two vectors. Okay, and that would be denoted as DIK, is the distance of waveform, signal waveform I and signal waveform K. So all these examples we are trying to explain that the continuous time domain signal operation can be replaced by the vector operations. using linear algebra. Okay, by using the linear algebra tools and theorems, and we can do the signal processing. So that opens the door of digital signal processing, right? From analog signal processing to digital signal processing. That is all because the signal is vectorized. Okay, the signal is vectorized, and the vectorized signal, the vector can fully represent original analog signal waveform. So how to find the basis? But the next question is how do we find the basis of the signal space given the set of waveform, right? So so that we can vectorize these waveforms, right? So the first steps to find the basis and therefore the signal space. The most common strategy is called orthogonal expansion of signals. First, say given a set of signals SIT, S2T to SMT, we can find a set of orthogonal bases. How we need to find the set of orthogonal bases to represent these M signals. The well-known strategy or the well-known procedure is called Gram-Schmidt orthogonalization procedure. Okay, the procedure is as follows. First, we can find the first basis by starting from the waveform 1, the first waveform S1T, and by normalize the normalize of this waveform, then we can immediately obtain the first basis is phi1t, and therefore S1T would be equal to square root of E1, the amplitude of the amplitude. E1 represent the amplitude of the signal. Okay, and so S1 would be represented by phi1t. So S1t, and we have phi1t, that is a normalized, is a normalization of S1t. Okay, and so then we continue on the second signal waveform, that is S2T. Let S2T be by remove the projection of S2T on phi1t. See, this is S2T, and there's a projection of S2T onto phi1t, and the projection is coefficient Ch3-1 phi1t, the part of S2T on phi1. and the difference, okay, the difference is the remainder is called R2T. It's a difference of S2T and its projection on phi 1. Okay, so that is R2T. Okay, that is R2T. So, and then we can then by normalize R2T, E2T, E2 is the power, okay, E2 is the energy of R2T, E2 is the energy of R2T. So by normalize the remaining signal of S2, then we have the second basis. Okay, then so we can see that now we have basis phi 1, normalized basis phi 1, and basis phi 2, and S2T is the combination of phi 1 and the combination of phi 2. Okay, and then we can continue on this procedure on S3T, right? S3T, and removing the projection onto the previous basis phi 1 and phi 2, and normalize the remainder of R3. Then we have R3, phi 3, and so on. So you can continue on the SIT, the waveform SI, and by removing the projection on previous basis of SI, and using the remainder of remainder I, then we can have basis phi IT. So by go through all the waveform from 1 to m, from all the waveform from M1 to M, then we can find a set of orthogonal bases, phi 1 to phi nt, that represent all the possible signal waveforms of all the S1 to SMT. So you may wonder, we do this procedure for all the M signals, right? So why we are not having M bases, but N bases, N, okay? The number of bases N is equal or smaller, okay? Equal smaller than the number of waveforms M. Right, it is because that in the procedure, it could happen that some signal can be fully represented, right? The remainder is 0, and a certain a waveform can be fully represented by the previous formed basis. Then the remainder is 0. Then and in that step, we do not have a new basis. Okay, so in that case, we have a smaller number of bases than the number of waveforms. Okay. So N is less or equal to M. Okay, so by applying the procedure, given any set of the signal waveforms, we can obtain the basis. So, so let me ask you a question. Is the set of bases unique or not? Whether the set of bases unique? The answer is not. Okay, it's not unique. Okay, the set of bases we found, okay, is highly dependent on the order that we apply to find the basis, on the order we apply on the waveforms. We can apply starting from S1, S2 to Sm. Then we have one set of bases. Or you can reversely, you can start from Sm and Sm minus 1 and to S1, right? Reverse order. Then we can find another set of bases. And actually, we can have any different orders on the M waveforms, right? And so different order that gives different bases, different set of bases. So the set of bases are not unique, but what is in common? The common is that no matter how we all reorder the procedure, all these different set of bases that represent the same signal space, okay, the span of different bases that gives the same signal space of dimension n to represent this set of signal waveform of m different waveforms. Okay. Okay, so far we have the fundamental concepts about the signal space and signal representation, and then we can vectorize the signal. So next we discuss the different type of modulations. First is the modulation with memory, and the modulation without memory first, and then modulation with memory. Okay, so let's discuss the most basic about what is digital modulations. Okay, the digital modulation, that means what's the difference of digital modulation and analog modulation? Okay, the digital modulation is a mapping of digital sequence into a set of waveform. Okay, so the input, okay, the input is digital sequence, the input to the digital modulator are digital sequence, or maybe just binary sequence. Okay, so it's called digital modulation. If the input is analog signal, then this modulator is called analog modulation. And because the input is the digital sequence, and then output is a modulation symbol. So this is called digital modulation. And we are trying to map this digital binary sequence into m different waveforms. What does that mean? Say we have the system offer m different waveforms, right? That represent m different message, and we have a binary sequence for transmission. Its BK is 0 or 1, and the bit rate is 1 over TB. And then every k bits that m equal to 2 to the k. So every k bits information that maps to one symbol. So each symbol represent k bits, and we have m symbols. Okay, and these symbols that goes to a pulse shaping filter GT, and that gives the transmission waveform. So the ST, okay, so ST is the in each time symbol, HT, each time symbol T, HT is certain, is one of the waveform, one of the symbol, one of the symbol is transmitted, and over different time symbol of I, that gives all the transmission waveform. And we have m different symbols. So here GT is called the pulse shaping function. An ideal, and not ideal, a very simple pulse shaping function is like a rectangular function that gives the most simple pulse shaping function. So what is modulation? The modulation process is to embed the message, right, the discrete time message info into a symbol, okay, the amplitude, phase, or frequency of the symbol, okay, of the symbol. That is called digital modulation. And the signal waveform would then bears the information of the bit stream. And each symbol contains represent k bits. And the symbol rate, okay, the symbol rate is the T is the symbol time, TB is the bit time. So every T equal to k TB, k bits. And the symbol rate would be 1 over T or 1 over KTB. As we said, the modulation schemes can be classified by different ways. We can by memory, could be with memory. That means that the mapping between the bit stream and the symbol depends on the past symbol. That means that the previous symbol that together determine the mapping. That is, for example, like differential modulation, the MSK, we will discuss this, and the continuous phase modulation, and so on. And without memory or memoryless modulation, that means that the mapping of the k bits onto the symbol depends only on the current set of the k bit and the symbol only. And it's like, for example, like amplitude modulation, phase modulation, quadrature amplitude modulation, and multiple M-array phase shift modulation. We can also categorize, classify the memory by linearity. By linearity, we means that it could be linear modulation or nonlinear modulation. The linear modulation, we means that the mapping satisfies the superposition principle that we mean, what we mean by linear modulation. So what do we mean by superposition principle? That means that if the A1 is a mapping to B1, A2 is a mapping to B2. Given these two mapping, then the addition of A1 plus A2 would give the mapping of B1 plus B2. Then we say this mapping satisfies the superposition principle. And by this principle, you can verify whether a modulation is linear or non-linear. For example, like NTHU modulation is a typical linear modulation. And so if a modulation does not satisfy the superposition principle, then it is nonlinear, like phase modulation and frequency modulation. The third way to classify the different types of modulation is by coherence. We can classify the modulation into coherent modulation or non-coherent modulations. Coherent modulation, what does that mean? Coherent modulation means that the transmitter and receiver are synchronized in phase. Has the capability to synchronize in phase. That means that because the transmitter and receiver, there's a transmission delay, and there will be introduce a random phase in the modulation symbol. So if the receiver can correct this random phase delay so that the transmitter and receiver phase can be synchronized. For example, the receiver has a sophisticated phase lock loop so that it can lock the phase of the received signal so they can sync with the transmitter. And if the modulation require the capability, the phase synchronization capability, and this modulation is called coherence modulation. So, and it's like, for example, like phase modulation, like QAM, that the modulation that depends on requires the phase information, exact phase information, so that the receiver needs to be able to have phase synchronization with the transmitter. This type of modulation that is called coherent modulation. And and if the modulation does not require the phase coherence between transmitter and receiver, that does not need the synchronization requirement, And this type of modulation is called non-coherent modulation. For example, like differential PSK, okay, and for example, like a PAM, okay, that depends on the amplitude, not on the or FSK, okay. There's does not require the phase synchronization, then it's called non-coherent modulations. Okay, so in this book we try to introduce the different type of modulation by the memoryless or with memory or without memory. So first we discuss the memoryless modulation without memory, and one is called pulse amplitude modulation. That is, the modulation signal is totally depends on the amplitude. That means that the transmit signal waveform, is there's a carrier, okay. There's a carrier cosine 2 pi FCT, and there's a pulse shaping function GT, and there's AM that has m different levels of amplitude. So the waveform, the different waveform SM is totally determined by the amplitude. If there are m level of different amplitude, and this is called M array PAM. Okay, so there are m different levels, So and so then this AM would be equal to plus minus 1, plus minus 3, and plus minus m minus 1, and so on. So we have m different levels of amplitude that represent the signal. For example, k equal to 1, m equal to 2. This binary is 1 bit and 2 waveform. So the amplitude takes the value of plus minus 1. This is called 2 PAM, m equal to 2. For 2 bits symbol, and then we need 4 different waveforms, m equal to 4. And then the amplitude takes 4 different levels, plus minus 1 and plus minus 3. And so this is called 4 PAM. For example, in this multi-level signaling, okay, and this shows the signal amplitude. The pulse GT is a rectangular, and there are different level of amplitude AM, amplitude for each symbol waveform transmission. Okay, and there could be m. In this case, in this example, there are each waveform represent 2 bits. So, and there are 4 different levels: plus 1, plus 3, minus 3, and minus 1. Okay, 4 different levels. Each level represent 2 bits. And so, and with the carrier cosine 2 pi fct, with the carrier cosine 2 pi fct, then we have the transmission waveform at the SMT, the carrier modulated the PM signal. So on the top, this is called baseband PM signal. At the bottom, this is called carrier modulated PM signals. Okay. So in this case, the SMT is a one-dimensional signal. Remember, the signal space representation we have discussed. Now let's apply this signal space representation concepts to this MRA PAM. We have the SMT is one-dimensional signal with SMT and equal to AMGT cosine 2 pi FCT, and this would be equal to SM phi t. Here the basis, okay, we have M waveforms, right? And what is the basis of the waveform? What is the basis of the waveform? By applying the Gram-Schmidt orthogonalization procedure, right? Then by normalizing the waveform, then we have the basis. That gives the basis by normalization. And all different, and these bases are also normal. Okay, so we have one basis, and we have m different signals waveform, right? And fortunately, all these m different waveforms can be represented by this one-dimensional basis. Can represented by this basis, and so the signal space is one dimension. The one dimension signal space can fully represent this m different PM signal. For example, m equal to 2, then we have two levels. And this is a one-dimensional signal space, and we have two amplitude. S1, this amplitude S1 and S2. For m equal to 4, then we have four amplitude. Then we have the in the signal one-dimensional signal space, we have S1. Okay, we have S1, S2, S3, S4 should be here. Okay, I'm sorry. So we have four amplitude of S, four different projections, four different symbols. The SM represent the digital modulation symbols, SM. We have two symbols, S1, S2. We have four symbols, S1, S2, S3, and S4. So SM represent the symbols, and SM would be equal to AM times this scaling factor. Okay, and so the mapping between bits and symbols, the mapping between, as we said, there are every k bit has a mapping to one of the m symbols. Okay, there are m different symbols. Then each symbol could represent k bits. M equal to 2 to the k. And GT, and the GT is a pulse, and we have the transmit signal ST. Okay, and the there are different combinations of these k bits. Okay, and these m different symbols, and the mapping is called encoding. And so there could be, for example, we have k equal to 2. Okay, for example, we have 4 symbols, S1, S2 to S4. We have 4 symbols. Each symbol represents 2 bits, right? Each symbol represents 2 bits. We can represent these 2 bits. We can have encoding of the 0, 0 to S1, 0, 1, S2, 1, 0, S3, and 1, 1 to S4. We can have also different encoding scheme of B that has 0, 0, 0, 0, 1, 1, 1, and 1, 0 for the 4 symbols, right? It's fine. It's just a mapping, right? It's just a mapping. Which symbol represent which 2 bits? No, it's just a mapping. So there exists different way to do the mapping. There exists different way to do the mapping. So which mapping or which encoding is better, or there's no difference, right? That there's a questions. Okay, there's like in this example, this encoding A or B, which is better? And of course, you can find many more different encoding scheme that mapping to the 4 symbols, right? And so how do we do the encoding of the bits to the symbol? Does it really matters? So the Gray, the mathematician Gray, has proposed Gray encoding rule. This scheme, different encoding actually that gives different performance, give different result of performance. In these two schemes, actually scheme B would be better than scheme A, because scheme B satisfies the Gray encoding rule. The rule says that the adjacent symbol point, right? The adjacent signal point like S1 and S2 has better differ by only 1 bit. Why? So the encoding B would satisfy this rule because each neighbor symbols that is differ by only 1 bit, right? In scheme A, the symbol S2 and symbol S3, it differ by 2 bits. Okay, so scheme B is better. Why scheme B is better? The reason is that when the error occurs in a symbol, it most likely migrate to a nearby points. Okay, when we transmit one of the symbols and with noise and fading, it's more likely that when an error occurs, it's more likely that error have an error detection to the neighbors. Okay, so when the error occurs and the encoding that differ by only 1 bit, then the cost is only 1 bit. We have another bit is correct. It's a damage control concept. So with gray encoding, we could minimize the number of error bits when a symbol error occurs. So the symbol error rate, would depend on the minimum distance, the minimum distance of the symbol. The neighbor symbol distance is the minimum distance, so it's more likely to have an error. Okay, so when the neighbor error occurs, we can minimize the error, minimize the cost of error by gray encoding. The D minimum becomes smaller and smaller. Okay. And the next modulation is called MRA, quadruple amplitude modulation, QAM. If we consider the QAM can be considered as a two-dimensional PAM with orthogonal basis. Right, there are 2 bases, phi 1t and phi 2t. It's a two-dimensional basis. And the SMT of the MRA QAM that has amplitude on the I channel on the cosine and the amplitude AMQ on the Q channel or on the sine channel. And AMI, okay, AMI and AMQ would be belong to the takes the value plus minus 1, plus minus 3 until plus minus m minus 1. Okay, and then so with these m different signals, we can have the they fall onto the 2 bases, phi 1 and phi 2. Okay, cosine basis and sine basis, and the each signal SMT that is mapping to the vector SM. SM takes the value AMI and takes value of AMQ. That makes the so-called constellation of the MRA QAM. For example, this is 16 QAM. There are 16 modulation symbols on I channel and Q channel. And each symbol, okay, each symbol or each vector, okay, each vector is each symbol that would be a mapping of 4-bit information for the 16-QAM. So the transmitter of this MRA QAM that be each k bits that has a mapping to the one of the M symbols. Okay, the symbol SM represent the M-QAM modulation symbol, and the symbol takes two value on the one on phi 1 and one on phi 2 that contains SMI and SMQ, and the SMI would be loaded on the basis phi 1 and SMQ loaded on basis phi 2, and together and the GT that makes the transmit signal SMT. And we can easily find that because in MRA QAM, every signal, every symbol takes different average. It's different with the MPSK that every symbol has equal energy. For MRA QAM, the different symbol that could take different amount of energy, right? The inner symbols has require smaller energy, and the outer symbols require more energies. So to evaluate the energy efficiency, we can calculate the average energy by taking the average of all the symbols, right? By taking the average of all the symbols, that would be, then we can find that the average energy will be equal to M-1/3 times EG. And so know that QAM versus PAM and PSK. So far we have discussed these three different modulations. So let's take a comparison among these different modulations. The QAM improves the bandwidth efficiency of PAM, right? The QAM is a two-dimensional PAM, right? And so given the same bandwidth, PAM and QAM, they have the same bandwidth. However, the QAM would, because of additional Q channel, the QAM would improve the bandwidth efficiency as compared to PAM. And given the same energy, okay, if we give it provide the same energy, e.g., given the same energy, the QAM gives better utilization of the signal space or the constellation space than MPSK. So this is MPSK. As M increase, is the distance between the D minimum become smaller very quickly, because there are a lot of space is empty and are not used, and the average energy is EG/2. And for the same amount of modulation for M-QAM, the modulation when m increase, the distance, okay, the distance would be equal to square root of 2g. Okay, the distance is defined by Eg. The distance is defined by Eg. So if we increase the m, however the distance does not change. We have the same distance, this same minimum distance, okay, as m increase. Then we have, based on this d minimum, then the average energy would be equal to this much. Okay, so so if we compare the d minimum and the average energy, QM has larger d minimum. If Eg, if we have the same Eg, then QM has larger d minimum, and hence gives the better aero performance. So so you can think of the question that given this, if given the same average energy, okay, if given the same average energy, not Eg is the pulse energy. However, if we have the provide this, assume that we have the same average energy, then you can compare the d minimum of MPSK and MQuam. Okay, you can do this as your own exercise, or we can do it in the homework. The quant modulation can also be viewed as a combined modulation of PAM and PSK modulations. For example, in this m equal to 8, MRA QAM can be considered as two PSK at different PAM levels, two levels of PAM. And this square quant PAM, QAM, it could be considered as 3 layers, okay, 3 layers of 3 different amplitude of PSK. So this you can have a different angle, and you can rotate the face of each ring of the PSK, and it's all considered as a kind of QAM modulation. Okay, that's stop here for this lecture. Then we'll continue the lecture next week.